Hey everyone, I hope you're doing well today. In this video, let's simplify down the process of polynomial long division. If you remember how to do long division with regular numbers or standard algorithm for division, then doing it with polynomials is going to make a little bit more sense. Let me explain. Let's see how we can relate this problem of 312 divided by 4 to this long division problem of x squared plus 5x plus 6 divided by x plus 2. So for the 312 divided by 4, this is what the long division would look like, so we know the quotient or the answer to a division problem is going to be 78 here. Let's see how that looks and compares to the polynomial long division. Dividing this x squared plus 5x plus 6 by x plus 2, you can see that there are some similarities with the process, and the quotient here is going to be the binomial of x plus 3. While regular long division has place values like ones place, tens place, and hundreds place, the place values for this polynomial long division are going to be constants, linears, and quadratics here. Just like it's important to keep place values lined up for regular long division, we're going to want to keep our terms lined up as well for polynomial long division. And before we get into some more detailed explanations and examples, we need to consider this. From this division problem, if we know that 312 divided by 4 is equal to 78, then it should also make sense that 312 divided by 78 is equal to 4. If that's true, then 78 times 4 is equal to 312, and we can also say that 4 times 78 is equal to 312. If that makes sense, let's try to see how that works with the polynomials now. If the trinomial x squared plus 5x plus 6 divided by the binomial of x plus 2 is equal to the binomial of x plus 3, then we should be able to say that x squared plus 5x plus 6 divided by x plus 3 is equal to x plus 2, and x plus 3 times x plus 2 is equal to x squared plus 5x plus 6, and x plus 2 times x plus 3 is equal to x squared plus 5x plus 6. Now that we got the basics out of the way, let's go through one example where we have no remainder and one example where we do have a remainder. Let's try dividing this cubic polynomial of x cubed minus x squared minus 22x plus 40 by this binomial of x minus 2. We'll start by setting up our long division by putting that first polynomial inside the division house and put that x minus 2 binomial outside as the divisor. To help you get started, it's really important to understand the degrees of our polynomial. So we have a cubic one on this inside, and what we're dividing by is going to be this linear or raised to the first power. The reason why it's helpful to know the highest degree of each polynomial is because if we're dividing something that's x to the third power by something that's x to the first power, we know that the highest degree of our quotient or answer is going to be x to the second power. In addition, it's important that our polynomial inside here is written in standard form in decreasing order. So we have this 3, we have this 2, we technically have a 1 here, and for this 40, this is really 40x to the 0th power. Since x to the 0th power is just equal to 1, we don't write it, but it has to be in decreasing order. If we're missing one, I'll go into that in another video in the future, so stay tuned for that. In this video, let's go ahead and just practice this one that has everything set up nicely. Then, to be super clear, I'm just going to draw these lines to help show you where our degree separation are going to be. And because we know from earlier that our quotient has to have a highest degree of 2, we know that our quotient is going to start on top of this x squared. So for this leading term, let's try to find a monomial that we can multiply by this x to the first power to match this x cubed perfectly. They both have a coefficient of 1, so what we're going to do here is put this x squared on top. Then, just as we planned, multiplying this x squared by this x to the first power, that's going to be 1x to the third power, we'll write that right underneath the x cubed, and then multiplying this x squared by this negative 2, that's going to be negative 2x squared. Then, just like normal long division, we have to go ahead and subtract to see what our remainder is going to be. Subtracting x cubed from x cubed, this will cancel out as planned. And taking this negative x squared minus negative 2x squared, that's going to be a positive 1x squared. Next, we're going to go ahead and bring down this negative 22x to join this x squared. And we're going to go ahead and repeat the process and try to find a term that we can write over here, so that when we multiply it by this x to the first power, it matches this x to the second power. Writing a positive 1x as this term, let's see if this works. Multiplying this positive x to the first power by this positive x to the first power, that's going to get exactly what we wanted, this positive x squared on the bottom. And then if we go ahead and take this positive x, multiply it by this negative 2, that's going to equal negative 2x. Or we can write a minus 2x down here. Just like earlier, we're going to go ahead and subtract these from each other to see what our remainder is. This x squared minus x squared cancels out just like we planned. And this negative 22x minus negative 2x is going to equal negative 20x. Well, that's our remainder so far. We have this plus 40 we can bring down to do it one more time. Let's go ahead and bring that down and try this process again. For this last term, which is going to be a constant, let's see what we can multiply by this x to the first power to perfectly match this negative 20x to the first power. Going ahead and writing a minus 20 here as our constant, let's see if this works. Multiplying this negative 20 by this x to the first power, that's going to equal negative 20x. We'll write that down below. And multiplying this negative 20 by this negative 2, a negative times a negative is a positive, so it's going to be positive 40. And repeating this process and subtracting one more time, let's go ahead and see what our remainder is going to be. Negative 20x minus a negative 20x will cancel out, and a positive 40 minus positive 40 also cancels out, so our remainder is 0 here. Putting this all together, we can see that our quotient is going to be this quadratic polynomial of x squared plus x minus 20. And if you wanted to check this, you totally could. If you took this x squared plus x minus 20 and multiplied it by this binomial of x minus 2, you would get the original polynomial of x cubed minus x squared minus 22x plus 40. Well, that's an example of a polynomial long division problem that doesn't have a remainder. Let me show you one that does. Let's go ahead and try to divide x cubed plus 4x squared minus x plus 1 by the binomial of x plus 3. So here's the problem set up. The degrees of our polynomial on the inside are going down nicely as 3, 2, 1, and 0. Remember, that's got to be important. And on the outside, we have this x to the first power, so we know that we have a linear term on the outside. That being said, if we have a highest degree term of x cubed on the inside dividing by an x to the first power on the outside, we know that our quotient is going to be the highest degree of x to the second power. To find the first term or the quotient to our answer, we need to find a term that multiplies by this x to the first power, so it matches this x to the third power. And what I'm thinking is 1x to the second power. If we go ahead and multiply this x to the second power by this x to the first power, that's going to be exactly x to the third power, which is what we wanted. And multiplying this x to the second power by this positive 3, that's going to be positive 3x squared. Then subtracting to find out what a remainder is going to be. These x cubes are going to cancel out as planned, and this positive 4x squared minus positive 3x squared is going to be a positive 1x squared. So while there's a remainder, we can go ahead and bring down this minus x to join it to repeat the whole process again. To find a term to put over here, we need to find something that multiplies by the x to the first power over to the left, so it matches this x squared in the front. Writing a positive x in this spot, we can see if this works. Positive 1x times a positive 1x to the first power is going to be x to the second power, and then going ahead and multiplying this positive 1x times this positive 3, that's going to be a positive 3x. Going ahead and subtracting to find the remainder, let's see what we get. These x squareds are going to cancel out as planned, and this negative x minus a positive 3x is going to equal negative 4x. Bringing down this positive 1, we can do this one more time. So let's go ahead and write this plus 1 next to the negative 4x and try to find one last term. For this last spot, let's try to find a term that multiplies by x to the first power to match this negative 4x to the first power down below. Putting a constant of minus 4 or negative 4 over here, let's see how this works out. Negative 4 multiplied by this x to the first power is going to be negative 4x to the first power. That's good. And multiplying this negative 4 by this positive 3, that's going to equal negative 12. I can go ahead and write that down below. Let's see what happens when we go ahead and subtract these from each other to find out the remainder. Negative 4x minus negative 4x cancels out, and positive 1 minus negative 12 is going to equal positive 13. At this point, we're all done. We just need to see how we can write our answer. To begin writing our answer, we're going to take the most important parts, or this x squared plus 1x minus 4. But to show how to write a remainder, which is this 13 down below, we're going to go ahead and write that as a fraction over this x plus 3 to show us what our remainder is. Since we have a positive 13, we're going to write plus 13 over x plus 3. Whenever you have a remainder, be sure to write it as a fraction over the divisor or that binomial or polynomial on the outside of the division house. And to hopefully make this a little bit more clear, let me show you a long division problem with regular numbers that also would have a remainder and what you would do. Imagine you had to take the number 437 divided by 5. So setting up this long division problem, we would write this 437 and divide it by this 5 on the outside. 5 is not going to fit into this 4, but it will fit into 43 8 times. So we can put an 8 on top. 8 times 5 is going to be 40. Those 4's match, just like in our polynomials. And then 3 minus 0 is going to be 3. We're going to bring down the 7 to join the 3. And we're going to repeat the process. 5 goes into 37, I think 7 times. 7 times 5 is going to be 35. And we're going to have a remainder of 2. Now, if we wanted to keep going and write this answer as a decimal, we could, and we would get 87.4 if we kept on going and adding zeros and decimals. But if we wanted to write our answer as a fraction like we do with polynomials, we know that this 5 goes into 437, 87 whole times, but take a look at the remainder here. The remainder here is going to be 2 over 5, right? So we can say that our remainder here is going to be 2/5, so it's 87 and 2/5, or 87 plus 2/5. Just like our polynomial long division problem. So while polynomial long division looks a little bit intimidating, hopefully this helps you feel a little bit better about it by relating it to normal long division with regular numbers. Hopefully you found this video helpful, and if you're looking for some extra practice problems, stay tuned for a future video where I'll go through a bunch of polynomial long division. And as always, keep up the great work, and I'll see you in the next one.